Sun is now flying in an unexplored region in space between the stars. NASA scientists are calling this a historic leap into space.
Voyager 2 detected abrupt differences in plasma density and magnetic particles upon crossing the heliopause.
Even from the moment Voyager 2 unfurled its first delicate instruments beyond Earth's warm embrace, there was an unspoken certainty among scientists and dreamers that one day it might reveal something so extraordinary or so momentous that the very nature of our understanding of the cosmos would shift. For 46 years, the probe drifted onward, its radio signals whispering tales of gas giants, distant magnetic fields, and the silent reaches of interstellar space. And then came the moment, an impossible discovery. One that no orbiting telescope, no Earth-based array, and no imaginative model had ever predicted. What it uncovered defies everything we thought we knew about the nature of the interplanetary and now interstellar frontier. Before we start, hit the like and subscribe buttons for more exclusive news. It began with anomaly detection routines aboard ground stations when signals from Voyager 2 arrived with an unfamiliar signature, a pattern of data that didn't conform to the expected cosmic background radiation or charged particle flux it had reported in the past. Engineers and scientists combed through decades of telemetry to rule out error. Was it instrument drift, radioactive decay in the electronics, cosmic rays corrupting data packets, or a software glitch? Yet as confidence grew in the integrity of the data, a slowly dawning realization took hold. Voyager 2 had encountered something unprecedented. The discovery erupted in startling clarity. The probe had crossed a boundary of physics, a region where particles were behaving in a way incompatible with existing models of the heliopause or interstellar medium. Specifically, Voyager 2 detected magnetic oscillations at frequencies never before observed in deep space, frequencies that implied an energy source and field structure unlike anything in planetary magnetospheres or typical solar-wind interactions. These were coherent oscillations, rhythmic in nature, as though cosmic waves were singing in a language entirely new to us. For the team on the ground, the implications were staggering. These oscillations suggested a celestial phenomenon, a structure or process operating on scales and energies that had until now been relegated to the realm of theoretical speculation. Perhaps a remnant of a previous epoch in the Sun's history, a fossil magnetic filament preserved in the interstellar medium, or alternately, evidence of a hidden population of massive, cold, charged dust grains, aligning magnetic fields like a cosmic harp. The possibility that this was the first direct measurement of extragalactic magnetic field remnants within the solar environs stirred both excitement and caution. In many ways, Voyager 2 had become a messenger, carrying back to humanity a communique from the unknown. For nearly half a century, it left our world, crossing planetary orbits and navigating heliospheric boundaries. Now it returned, not in person, but through the pure language of data, with a signal that challenged the boundaries of physics. What it found may not immediately rewrite textbooks, but it compels us to open them in new places. The mystery of those oscillations points toward phenomena that could inform everything from cosmic ray propagation models to the nature of cold interstellar matter and the evolution of astrophysical magnetic fields. Imagine the cosmic waves that encountered Voyager 2, unseen, unheard, and until now, unimagined. They may ripple through the interstellar medium, threading particle flows with energy, helping shape star formation regions, or even acting as seeds for magnetic scaffolding in newborn galaxies. If these oscillations prove to be widespread, they may offer clues about how galaxies sustain and organize their magnetic fields across eons. Alternatively, if they prove to be local to our solar neighborhood, a unique interaction between our heliosphere and a filament of interstellar material, they would illuminate the complex boundary region where solar and galactic influences intertwine. The simple act of detecting coherent magnetic oscillations at such frequencies demands new lines of inquiry. Laboratory plasma physicists may seek to replicate conditions in specialized setups, attempting to recreate electromagnetic resonances with dusty plasmas threaded by magnetic fields. Astrophysicists will reach for new models, whether those involve magnetohydrodynamic waves in cold, neutralized plasmas or exotic dust grain dynamics in tenuous media. Theoretical physicists could find themselves reevaluating long-held assumptions about how energy transfers occur in a sparse plasma lacking traditional drivers, like shocks or turbulence. This discovery doesn't just open new questions, it opens entirely new chapters in the physics of the cosmos. At a human level, the notion that a probe launched in 1977, carrying with it a golden record and a bit of Earth's curiosity, could one day report back the first signs of a phenomenon nobody had predicted resonates deeply. It reminds us that exploration, at its most profound, is about encountering what surprises us. There is something poetic in the thought that, after decades of drifting through darkness, Voyager 2 has illuminated a corner of reality that no human mind had glimpsed before. The universe, it seems, still reserves its greatest revelations for journeys that persist through time and distance. The discovery also underscores the importance of long-duration missions. In an era when attention often flits from one dazzling spectacle to another, planetary landings, space telescope images, ambitious new probes, Voyager 2's revelation is a powerful argument for patience and perseverance. Some truths reveal themselves only to explorers who linger on the margins for decades. It elevates the notion that science is not just about bold leaps, but also about steadfast presence in places where the cosmos whispers secrets at length. Questions now multiply. Are the oscillations transient or persistent? Do they vary with Voyager 2's changing orientation or radial distance? Are there subtle correlations with cosmic ray intensity or local density fluctuations? Could Voyager 1, if still sampling nearby space, confirm or refute the presence of similar signals? What exactly is creating that coherence? Charged dust grains, magnetic filaments, or some still unknown mechanism blending charged particles with electromagnetic fields? Astronomy and astrophysics communities worldwide will now pore over the data, cross-checking with observations of local interstellar clouds or magnetic anomalies detected by other probes. Researchers studying cosmic dust, interstellar turbulence, magnetic field mapping, and heliophysics will find themselves in dialogue as never before. Collaboration may extend across disciplines, from earthbound plasma labs to radio astronomy observatories mapping polarized interstellar emissions, to theoretical teams crafting new simulations. The magnitude of this discovery is not just technical, it is symbolic. Voyager 2, humanity's farthest flung emissary, reaches across cosmic distance only to return the most intimate gift, an insight into the unseen patterns of the universe. It reminds us that curiosity, once launched, keeps yielding even decades after liftoff. There's a kind of beauty in knowing that a stream of electrons and magnetism, generated billions of miles away, travels across space and time to reshape our understanding of what lies between the stars. This breakthrough encourages new questions about what other surprises might lurk in the edge of our solar cocoon. Could similar phenomena await detection at the boundary of the heliopause or deeper in the interstellar expanse? Phenomena that are quieter, subtler, or more exotic than we imagine. Could our own sun's history have left behind fingerprints, magnetic or particulate, that continue to interact with the heliosphere in unexpected ways? These are mysteries that demand not only our attention, but also bold plans. New missions that follow in Voyager 2's wake, instruments designed to detect low-frequency oscillations, dust-plasma interplays, and magnetic field waves in unexplored regimes. This discovery is a call to imagination, reminding us that space exploration is as much about listening as it is about seeing. Voyager 2 did not send back a photograph or a visual spectacle. It sent back an echo, a pattern, a whisper that invites us to listen more deeply. It shows how even in the silent, dark vastness of interstellar space, there are rhythms waiting to be heard, cosmic melodies that may turn out to be the score for forces shaping galaxies. The cosmic horizon has grown richer with meaning. Those oscillations recorded by Voyager 2 are not merely data. They are a key to understanding the scaffolding of magnetism and energy in the lightly trodden realms beyond the heliosphere. Even as the probe continues to fade in power, those signals will continue to speak. And as our instruments grow more sophisticated, perhaps we will learn to translate their language more fluently. Voyager 2's impossible discovery reminds us that sometimes the universe speaks quietly, and when we listen with patience and precision, it shares its deepest wonders. The implications reach beyond astrophysics too. They touch philosophy, the quiet persistence of a probe powered by radioisotopes, reaching farther than we ever imagined, unveiling something unanticipated about the cosmic neighborhood, forces one to reflect on the vastness of reality and the smallness of our assumptions. It invites us to consider that our frameworks, however elegant, are always provisional, subject to the caprice of surprise. The story of Voyager 2's discovery will soon ripple through classrooms, lecture halls, and popular dialogues. It will inspire a new generation of explorers, those who hear that announcement and think, if Voyager 2 can find something impossible after 46 years, what might our generation uncover if we venture farther, listen harder, and wait longer? The news carries a challenge for future mission designers and funders. Durable spacecraft with tenacious lifespans, instruments tuned for whisper frequencies, and missions aligned not just for immediate returns, but for decades of potential revelation. And while we await the careful analysis, modeling, and perhaps even lab recreation of these oscillations, we can hold the wonder of this moment, that an object launched when digital watches first became common has now become the first to contact a new form of cosmic music. Voyager the 2nd of May be silent soon, but its message sings on, and that melody reshapes how we see the cosmos. The signals that came back from Voyager 2 have done more than simply spark scientific curiosity. They have pushed the boundaries of how we define the known. For decades, scientists have relied on models that map the heliosphere's interaction with the interstellar medium, treating it as a relatively stable interface where the sun's influence tapers off and gives way to the galactic environment. Voyager 2's latest detection breaks that assumed stability. It suggests that the frontier is not a clean border, but rather a dynamic, complex region that can sustain intricate physical processes capable of generating phenomena never before recorded. These newly observed oscillations hint at the existence of vast regions of space where forces act in concert over extraordinary distances, manipulating matter and energy in ways that defy standard expectations. If they are tied to a filament-like structure threading through the interstellar medium, the sheer scale of such a feature could be staggering, stretching for light years, possibly connecting star systems in a kind of invisible web. This revelation forces a reconsideration of the solar system's neighborhood, transforming it from an empty void punctuated by isolated stellar systems into a textured environment filled with unseen frameworks of magnetism and energy. The idea that these oscillations could be part of a persistent, large-scale network introduces fascinating consequences for our understanding of cosmic connectivity. If magnetic structures extend between systems, they may serve as conduits for charged particles, potentially influencing the flow of cosmic rays into the heliosphere. This would have profound implications for astrophysics and space weather studies, as the sun's exposure to such channels might fluctuate over time, subtly affecting everything from planetary atmospheres to radiation levels on distant worlds. Another possibility, one no less captivating, is that Voyager 2 has stumbled into the wake of an ancient stellar event. Imagine a supernova that occurred hundreds of thousands of years ago, its shockwave expanding outward through the galaxy, compressing interstellar gas and magnetizing it. Over time, those remnants would weaken, but pockets of enhanced magnetic structure might persist, carrying with them the fingerprints of that explosive origin. If this is the case, Voyager the 2nd of May have inadvertently recorded the faint echoes of a cosmic catastrophe that occurred far beyond the sun's birth cloud, its energy now woven into the quiet spaces between stars. From a technological standpoint, the very fact that Voyager 2 was able to detect such subtle features underscores the remarkable durability of its design. It was never built to operate in this regime of space or to sense phenomena on this scale, yet its suite of instruments, carefully calibrated and maintained through decades of command uplinks, proved capable of catching a signal so delicate that even Earth's most advanced telescopes might miss it. This shows the extraordinary value of engineering foresight and the importance of building spacecraft with the capacity to exceed their intended missions. The lesson here is simple but powerful. The further you go, the more unexpected your findings will be, and the more you must trust in the robustness of your instruments. If the oscillations do represent an entirely new class of interstellar phenomenon, there will be profound ramifications for our theoretical frameworks. Standard magnetohydrodynamics assumes certain energy dissipation rates, wave modes, and plasma stability conditions in the low-density medium between stars. This discovery may point to exceptions, instances where energy is sustained far longer than models predict, perhaps due to novel plasma instabilities, or a feedback mechanism between charged particles and magnetic structures. Such exceptions could play a role in shaping the evolution of the interstellar medium over vast spans of time, influencing how material condenses into new stars or disperses into the galactic background. There is also an alluring possibility that these coherent oscillations might be part of a larger cosmic-scale symphony, an interplay between multiple astrophysical processes operating over immense distances. If localized magnetic fields are periodically modulated by passing shockwaves, streams of charged dust, or gravitational disturbances from massive objects, then Voyager the 2nd of May have just intercepted a fragment of this broader orchestration. Mapping this out would require correlating its data with observations from other spacecraft, Earth-based observatories, and even radio telescopes tuned to the right frequencies. For planetary scientists, the discovery could be a treasure trove of indirect clues. If similar oscillations influence the propagation of cosmic rays, they might also subtly affect the chemical evolution of planetary atmospheres over millions of years. Variations in cosmic ray flux can drive changes in atmospheric chemistry, alter cloud formation, and possibly impact the habitability of worlds within affected regions. This raises questions about whether certain planetary systems experience long-term climate influences due to their position relative to such magnetic structures. Voyager 2's journey has, in essence, revealed a layer of complexity to interstellar space that transforms it from a simple backdrop into a living, breathing environment. The data implies that far from being a void, interstellar space is teeming with structure and activity, much of it invisible to human senses and only accessible through persistent, long-range exploration. The oscillations could mark just one of many hidden processes shaping the galactic environment, waiting to be uncovered by patient instruments drifting on the far side of the heliopause. The implications extend to our understanding of cosmic ray shielding. The heliosphere acts as a partial barrier against high-energy particles from interstellar space, but if there are regions where magnetic oscillations modify particle pathways, then the shielding effect may vary depending on the sun's motion through the galaxy. This could mean that Earth's radiation environment has experienced periodic fluctuations over geological timescales, potentially aligning with other long-term cycles observed in climate and biosphere evolution. Even the philosophical resonance of this discovery is profound. For generations, interstellar space was imagined as a silent emptiness, a vast nothing between the stars. Voyager 2's findings disrupt that vision, suggesting instead a domain rich with unseen order. It invites us to imagine space not as a void, but as a medium alive with patterns, each one a relic of ancient forces and cosmic events. That shift in perspective is as much a leap for human imagination as it is for astrophysical theory. On a more practical level, the detection of coherent oscillations opens a new observational window. With the right instruments, future missions could deliberately target these frequencies, mapping their distribution across different regions of the galaxy. By studying how their characteristics change with position, scientists could build a three-dimensional picture of the interstellar medium's hidden architecture. Such work could yield insights into how the galaxy's magnetic field evolves, how matter moves between stars, and how energy is stored and transferred across vast scales. Voyager 2's data may also prove invaluable in refining our models of the heliosphere itself. The interaction between the solar wind and interstellar material is far more complex than previously believed, and these oscillations might represent a form of energy exchange at the boundary. If so, the heliopause is not a simple dividing line, but a semi-permeable membrane through which information and influence pass in both directions. Understanding this process could reshape our approach to predicting the sun's interaction with its galactic environment over the next tens of thousands of years. The sheer patience required to arrive at this discovery cannot be overstated. For nearly half a century, Voyager 2 traveled outward at tens of thousands of miles per hour, carrying with it the hopes of an era. Most missions have lifespans measured in years. This one persisted through generations of scientists and engineers across changes in technology, politics, and culture. That endurance speaks to an essential truth about exploration. Sometimes the most important discoveries come not to those who rush, but to those who wait. As scientists pore over every byte of the new data, they must also wrestle with the tantalizing ambiguity it presents. The oscillations are clear, but their source remains elusive. It is possible that their true explanation will require an entirely new branch of space plasma theory, or that they will be tied to processes we have glimpsed elsewhere but never connected to interstellar space. In either case, the next steps will involve building theoretical bridges between the known and the unknown, using Voyager 2's measurements as the foundation for an expanded map of cosmic behavior. Beyond science, this event carries a cultural significance. Voyager 2 is one of humanity's most iconic emissaries, carrying a physical record of Earth's sounds and images into the depths. Now it has returned with a message of its own, one that no one on Earth could have scripted in advance. It reminds us that the act of sending something into the unknown is inherently an act of faith. Faith that the universe has more to reveal than we can predict, and that the instruments we build may one day hear something unexpected. The importance of such surprises cannot be underestimated. Science thrives on prediction, but it advances through anomaly. The moment something doesn't fit, the moment the universe whispers, "You didn't expect this," the boundaries of knowledge shift outward. Voyager 2 has delivered such a moment, and the ripple effects will spread through multiple disciplines in the years to come. It's easy to forget, in an age of rapid technological turnover, that the signals we now celebrate were captured by an antenna launched before most of today's scientists were even born. The data's journey back to Earth spanned more than 18 billion kilometers, crossing the cold void to be received by massive radio dishes on our planet. Every bit of it traveled through regions of space that no human-made object had ever traversed before. That physical reality, that these readings were taken in a place utterly beyond our reach, imbues them with a certain gravity, a reminder of the vastness that still lies beyond our grasp. Voyager 2's encounter also emphasizes the value of redundancy in exploration. Without its still functioning instruments, this phenomenon might have remained undetected for decades, perhaps even centuries, until another mission ventured far enough to find it. The fact that Voyager 1 and Voyager 2 traveled along different paths means that we now have a chance, however slim, to compare data from two separate locations in the interstellar medium, potentially distinguishing local features from widespread ones. What comes next will be an extended period of hypothesis and testing. Researchers will attempt to simulate the conditions Voyager 2 encountered, examining whether similar oscillations can emerge from plasma flows interacting with magnetic structures. They will explore whether dust particles could be charged in such a way as to sustain oscillations over great distances, or whether shockwaves from ancient stellar events could set up resonances that persist for millennia. Each of these possibilities carries implications that reach far beyond the detection itself, touching on fundamental processes that shape the galaxy. If further study confirms that such oscillations are common in interstellar space, they could become a new tool for mapping the invisible. Much like how seismologists use earthquakes to probe Earth's interior, astrophysicists could use these cosmic oscillations to probe the structure of the galactic medium. By analyzing how the waves propagate, reflect, and dissipate, we could gain an entirely new perspective on the hidden landscapes between stars. There is an additional layer to this event that goes beyond the mechanics of magnetic fields and plasma physics, the way it reframes our sense of time and exploration. The signals Voyager 2 detected have likely been present for far longer than humanity has existed. They did not begin when our spacecraft arrived. Rather, we arrived at the right place to notice them. This means that deep space may be threaded with ancient processes, ongoing for millions or billions of years, whose continuity dwarfs the entire timeline of human civilization. It forces us to consider exploration not only as a search for the new, but as a moment of intersection, where our brief presence overlaps with the timeless rhythm of the universe. This perspective changes how we think about deep space missions. Instead of seeing them as isolated bursts of discovery, they become points along a continuous tapestry of phenomena that will endure long after our instruments fall silent. Voyager 2's encounter suggests that the true challenge is not necessarily to find events happening now, but to place ourselves in positions where the eternal patterns of the cosmos become visible. This demands planning on a scale that few endeavors on Earth require. Missions conceived not for years or decades, but for lifetimes and beyond. The fact that such a phenomenon was uncovered by a probe launched in the 1970s adds a quiet, humbling lesson about the unpredictability of discovery. The mission's original objectives were planetary flybys, its route carefully chosen to exploit a rare alignment of outer planets. Nothing in its blueprint explicitly aimed at finding coherent oscillations in the interstellar medium. And yet, here we are, looking at data that may reshape our understanding of space physics, precisely because the probe was allowed to keep going long past its anticipated end. This is a stark reminder that the most valuable returns sometimes come from the unscripted chapters of a mission. In thinking about the broader implications, one cannot ignore how this event could influence the design of future deep space probes. Until now, many missions beyond the heliosphere have focused on measuring particle densities, magnetic field strengths, and general environmental conditions. Voyager 2's detection suggests that we may need to prioritize sensitivity to subtle, low-frequency phenomena, signals that are faint and long-lasting rather than dramatic and transient. Instruments capable of teasing out such faint patterns from the surrounding noise could become standard for interstellar explorers of the future. There is also a navigational aspect to consider. If coherent oscillations are indeed tied to vast magnetic structures or filaments in the interstellar medium, they could potentially serve as beacons for navigation beyond the solar system. Just as sailors once used the predictable positions of stars to orient themselves, future spacecraft might use these cosmic oscillations to determine their position relative to large-scale galactic features. This could revolutionize autonomous navigation in deep space, reducing reliance on Earth-based tracking and allowing probes to roam farther with greater precision. From the standpoint of comparative astrophysics, the discovery also raises the intriguing question of whether other star systems exhibit similar phenomena at their own boundaries. If our solar system interacts with the interstellar medium in ways that generate or reveal such oscillations, then by extension, other systems may produce their own unique signatures. Observing these could offer clues about a star's magnetic history, its wind patterns, and even the properties of its surrounding galactic environment. Such observations might eventually allow astronomers to distinguish between different types of stellar neighborhoods without having to send probes to each one. The detection's value also extends into the search for life, though indirectly. While magnetic oscillations themselves may not be linked to biology, the structures that generate them could influence the habitability of planets within a given system. If such features alter the flow of high-energy particles, they could affect how atmospheres evolve, how surface radiation levels change over time, and how stable a planet's climate remains over geological periods. By better understanding these influences, scientists might refine the criteria for identifying worlds where life has the best chance to emerge and endure. This moment with Voyager 2 also touches on a deeply human impulse: to leave a mark on the unknown. The golden record it carries was intended as a gesture toward any beings who might one day encounter it. But in a way, the spacecraft has now brought something back to us instead, a marker from the universe itself. It is as though the cosmos has answered our greeting, not in words, but in a pattern of magnetic waves that only the patient ears of a far-flung machine could hear. This interplay between what we send outward and what comes back inward lies at the heart of exploration's enduring appeal. One must also recognize that the sheer remoteness of Voyager 2's position adds a unique weight to the discovery. Every meter it travels is a meter no human has ever been to, no other instrument has ever occupied. Its findings are not merely academic, they are literal firsts, observations made from a point in space that will never again be replicated exactly. This singularity gives its data a quality akin to rare historical documents or unique geological samples, the kind that cannot be replaced once lost. The psychological dimension of this event is equally significant. It expands the mental map of where something can happen in space. Many still imagine the richness of discovery concentrated around planets, moons, or nebulae, visible, tangible targets. Voyager 2's new detection is a reminder that empty-looking space is not truly empty, and that between the showpieces of the universe lie vast regions alive with subtle, invisible complexity. In doing so, it may inspire a new generation of researchers to specialize in the science of the in-between, those areas once dismissed as voids but now revealed as dynamic environments in their own right. Finally, the enduring image of this discovery will likely be of contrast. The quiet hum of the oscillations set against the absolute silence of the surrounding space. The ancient persistence of the phenomenon against the brief spark of human detection. The fragility of the probe against the vastness of its environment. These contrasts sharpen the sense of scale and time that such a mission represents. Voyager 2's achievement here is not just in crossing a boundary, but in doing so with the grace of endurance, carrying human ingenuity into places where it was never certain it could survive, and returning with proof that the universe still holds mysteries willing to meet us halfway. If you liked this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us, what are your thoughts on Voyager 2's discovery after 46 years and what's next? We want to hear from you. Thank you for watching and see you next time.